Welcome back, everybody, on this rainy day. I hope you're doing fine. The topics for this week, as we also seen on Monday, I made a slight revision, and today the original idea was actually to start with the with two-body scattering, but actually I want to discuss some small bits and pieces which are relevant for the second midterm. So these are kind of small insights which allow you to interpret the results which you're getting. And then I also wanted to go through some practicalities about the midterm, how you can solve, for instance, the problem with the Earth, Sun, and Jupiter. Some of you may like to run everything in 3 dimensions, and I'm going to show you how you can do that. And then on Friday, we are going to dedicate the whole day, or I mean the whole lecture actually, not the whole day, but the whole lecture on the midterm. And the same thing with the next Friday, which is then the deadline for the second one. So there is no homework this specific week, there's only work on the midterm. So just let me also remind you of some small things. See, if you just click on the README file, you will find the solutions to various assignments. And for the second midterm, I mean, you peeping into what you did in homework 5 is very, very relevant. And you can actually reuse that code. If you're a little bit unsure whether your code was running correctly or not, you can always look into the solution to homework number 5. And then you've been coding many of these things again and again. You have done this in homework 8. You did parts of it in the first midterm. So you should be pretty familiar with the way you're setting up things now. And essentially what you see is a repeat of this kind of drill, where you find the forces, you find the acceleration, and then you integrate. So we've basically been doing that in almost every homework, actually. Now, so the thing which I wanted to do now is actually to look a little bit more into some small theoretical issues which are actually pretty neat and which may be helpful when you want to interpret the results. So one thing is to run the code and get some results, but then we as physicists, we always have to ask ourselves, what does this actually mean? Can I gain some insights by combining the results I get from running a code and perhaps, if we are lucky, the analytical solutions? And in this case, we do have analytical solutions. So let's look at some of these things which we discussed on Monday and remind ourselves of some of the features of the solutions, and then look at examples. And then at the end, we are going to go into some practicalities with the midterm, in particular, when we want to include Jupiter. And when you've seen the way you include Jupiter in your code, that's the way you would include the other planets. So if you have a program which functions with an additional planet, just adding more planets is just a repeat of that. The only thing which can go wrong is you punching in the wrong masses for different planets. And then I also wanted to show you where you can find the initial conditions for the planets. I mean, the positions and the velocities. So NASA has a website where you can actually fetch these. So you can run a more realistic simulation of the solar system with velocities and positions taken at a specific day. And that's pretty neat. Okay, so let's go back to the whiteboard and look at some of the things we did on Monday and try to transfer them to the way we are going to look at the results we get from the second midterm. Any questions so far? Things which are unclear? If you had problems fetching solutions, we're also going to hang around till 5 o'clock here. So if you wish to hang around, I mean, feel free to do that. Same on Friday. Okay, so no questions. So let's move over to the whiteboard and look at some applications of the theory which we developed on Monday. And so let me quickly remind you of some of the things we did on Monday. So one of the things which we have done is to define an effective potential, this V effective of R, which now is given in terms of the potential, which depends only on the relative distance between two objects. And then we've got this term which came from the kinetic energy, which gives a so-called centrifugal potential, and it acts like a kind of barrier. So this goes like a mu, which is the reduced mass. Let me quickly remind you of that. So we have two objects, mass 1 and mass 2, divided by the total mass here. So plotting that object, or this function here, as a function of the relative distance, the magnitude of the relative distance, we got something like this. And what we saw then is that we had 4 different types of situations where we had an R here. So this is the R min, as we called it. And in that specific case, we got circular motion. I'm just repeating what we had on Monday. This corresponded to this eccentricity, epsilon, which was defined as, and I'm just coming back to that one. So this epsilon was given by A, which is a constant in the solutions, L squared, divided by alpha times mu. And this alpha, so let me quickly remind you, this comes from the potential. So there's a minus alpha divided by R. We had a solution of R as a function of the angle, which is given as A plus, so we had, sorry for that, let me just rewrite it. So it was given by 1 divided by this mu, reduced mass, angular momentum squared, plus A times cosine phi. And we rewrote this one in terms of a new constant C of 1 plus epsilon times cosine phi. And this parameter C is now just determined in terms of the constants of the system, the angular momentum, which you can actually measure, for instance, for the Earth. It's pretty well measured. And then with this solution here, what we could do then is actually to go back and we could define a new R min. So one of the things which we discussed is that in this position here, we have a d of R dt, which is the radial velocity, which is equal to 0. So that means that this R min, we have only the angular velocity. Then if we had an epsilon, which took values larger than 0, but less than 1, we could define a new R min. And then we would have an R max here. And that would correspond to elliptical motion. So this is an ellipse. Sometimes my handwriting, this is an ellipse. And in this particular case, we had 0, less than epsilon, less than 1. And then we could define a new R min here. And in this specific case, we have epsilon 1. And that gave us a parabola. And the energy was equal to 0. So that's the total energy. So that's the sum of kinetic energy and potential energy. In the cases here, we had an energy which is less than 0. And then we could have a R min here. So that means that the two objects are getting very close. And you could think of this as a kind of turning points. And in this particular case, we had epsilon larger than 1. And then we got a hyperbolic motion. Hyperbola. So let me just spell this out correctly here. And this corresponded to an energy larger than 0. Now, one of the things which we did last time was actually to look at the potential, which we called a repulsive potential. We put a plus sign. And then we got a system which didn't allow any type of bound motion. So when we say bound motion, it means that you are confined to move around an object or an origin. And in our case, the origin is defined as the sun. Now, the thing we can look at now are some additional examples. So let's look at the next example here, example 1 today. And if we now have a circular orbit, then we know that we can find the velocity in terms of actually the constant in front of the potential. So we know that we have, if we have a circular orbit around a given, given by gravitational force, let's say the sun is your center, then the speed of the orbiting body is inversely proportional to the square root of the radius which we have. So let's look at that. Now, one of the things we know then, if we now think of the force, so in our specific case, the force is now given, and we are not specifying the term alpha, whether it's a positive or negative. So we know the force goes like this. So what we looked at was a case where we had minus alpha divided by r squared. So let's leave the sign of alpha unspecified, okay? So let's just write it like that. Now, what we know then is that also when we look at this centripetal acceleration, which is something which we looked at in the first midterm when we were to define whether we had circular motion or not, then we know that m times v squared divided by r, so this is the force, which follows from the centripetal acceleration. We know that the centripetal acceleration now is an acceleration a of r, or we call it the radial acceleration, and we know that that's given by the velocity divided by r. Now, this is now equal to the force, so this is equal to F. So which means that when we plug in F then, so we have mv squared divided by 2, so that becomes simply alpha divided by r squared. And that means that V, in this specific case, is actually given by alpha divided by m times r. So this is a pretty neat result. And when you are dealing with the midterm now, and you need to fix, let's say, the initial velocity, and you're running the calculations with radial coordinates only, then you know that this could be the definition of the initial velocity of the system. Okay, so let's look at another case. So let's take a next example. And in this case, what we're going to look at now is a force which is a little bit different. So let's take K, and we don't specify K yet with the sign of it. And we assume now that the force is K divided by R cubed. So that means that we have a potential V of R when we take the negative derivative with respect to R, which goes like K divided by 2R squared. There are actually such effective forces in nature. So we can parameterize specific interactions, and you could get a potential which goes like 1 over R squared. Now, the reason why I bring up this case is that in the midterm, you are actually asked to, in your program, to change the exponent of R. So when you change that one, you're going to get some odd behaviors. But this case is also a case which you can solve analytically. So when you run the numerics and you see the results you get, you can then go back to this example 2 here and then look at the analytical solution, because from that one, you can just say, okay, now I understand why the system behaves as it does. So this is one of the other cases where we can solve this two-body problem by transforming to relative coordinates and obtaining an analytical solution. And that's a pretty neat case. So let's see why we can get an analytical solution here. Now, if we now go back first to the effective potential, when we now have made a transformation to polar coordinates, we have this V of R, and in this case, this is K divided by 2R squared, and then plus L squared divided by 2M, or let's write this as a mu here, because that's the quantity we've been using. So we have a mu over R squared. Now it depends really on the value of this K. So this would be the same as K plus L squared divided by mu. And then I would have a 2 over R squared. So you can look at different cases now. So you could assume that K is less than 0 or larger than 0. The thing you notice now is that there is a common constant here. So this constant could be negative in total, and that depends on the value of this K and the value of the angular momentum. So depending on the value of the angular momentum and this value K, you can get a potential which gives repulsion or a potential which gives attraction. So you could get a situation which looks like this. So if you plot this potential, so one instance you could get is that you have V of F of R, which looks something like this. So that's one possibility, because now we are lumping together these constants. So what we're assuming then is that K plus L squared divided by mu is larger than 0, right? So that's a typical case, and depending on the value of K and L, so K could be negative, but L squared divided by 2 mu could be larger than L K negative, so that at the end, these two combined constants become larger than 0. Now, if you look at that case, if you now suppose now you're coming in here, remember again that this is a relative distance between two objects, and you placed one of the objects in the origin. So you're coming in, and then you come to a specific point here. That's the energy you're having. So this is your total energy, and this will be your R min here. And when you come in here, you're knocking on the door, and it says, no, no, you're not, you can't come closer, and then you're knocked out again, right? So that means that what happens in this type of motion is that you will be reflected at this point, and then you will move out again. Now, if you now think about what we analyzed previously, this is a case where the energy is larger than 0. So what kind of motion would you expect here? Yeah, hyperbolic motion, right? So you can make other types of combinations of K and L squared, so that at the end, K plus L squared divided by mu is less than 0. And then you would get a potential. If that is the case, then you would get a potential which looks more like this. So if we plot it, then we would have something which runs like this. So if you then have an R min here at specific energy, this is the minimum radius which you would have. And in that case, you would have a kind of bounded motion. And the energy would be less than 0. And that depends all on the constants which we have. So in this specific case, E is less than 0, then you would have a bounded orbit. Now, in the homework, you actually, in the midterm, you actually ask to run the calculations with such a potential, but you're going to make this numerical simulation. Let me now show you that you can actually get an analytical solution with a potential which goes like 1 over r squared. And that gives you a force which goes like 1 over r cubed. Whereas the gravitational force goes like 1 over r squared. Now, the reason why we've been looking at 1 over r cubed in the programs is because we have multiplied the force with a unit vector. So if we now look at these equations, what we are going to do now is just to remind ourselves of the way we solve the differential equation. So what we did in the differential equation, we, as a function of phi, we defined this function which was 1 over r equal to u. And then we had a differential equation, a second order one, which we, in the case of the gravitational force, we could solve it analytically. Now, if I do this now, what I get is so this is the general equation which we had when we solved the gravitational force problem. So we would have a times a mu here, divided by L squared, and multiplied with u squared. Now, in our case, this force, F, is now given by this constant K divided by R cubed, which is the same as K times U cubed. If I plug that one into the equation, what I get then is a d of U, second derivative, which is now equal to minus, and then I have 1 plus this term K times the reduced mass divided by L squared multiplied with U. This is nothing. If you think back to what you see here, we've seen this now many, many times, right? So what would the solution to this equation be? If you think of, these are just constants, which we have here, right? Yeah. Cosine and sine. So this is again, another harmonic oscillator, right? The same equations. And this leads to, when you see an equation like this, where this is just a constant times the unknown quantity here, then this gives a cosine sine, or an exponential if you prefer the exponential. So when you see something like that, you don't need to think anymore. You say, I just know the solution. So this case as well, when you have a 1 over r squared potential, that gives you a analytical solution again. So let's look at the analytical solution, because when we have this analytical solution, it's going to be easier to understand. And I think that's exercise 1E or 1D. I don't remember exactly which one it was. I mean, the first part of the midterm. So if you look at that one, we can now just sandwich this into a constant. And we could call this our natural frequency again. So let's just call this, because we have divided by the mass. So this could be our omega 0 squared, right? This is just a constant, which we have there. So it means that we have an equation of this type, minus omega 0 squared of u. That means that this u of phi is now given by some constant. Let's call it c over cosine phi times omega 0. Omega 0 times phi plus a constant d times sine of an omega 0 times phi. And we know that we could actually sandwich this one in terms of a more compact expression, where we have a new constant, which is omega 0 phi minus a phase shift delta. This is something which we did, I guess, the week before the midterm break. So if we now look at the radius, then the radius is actually 1 divided by u. So that means that what we have now is actually 1 divided by a times cosine of omega 0 phi minus delta. And we could now make an assumption that this k is larger than L squared divided by mu, just as an example. Then we know that the constant, what we have then, is that k times mu over L squared is larger than 0. So if you now look at the solution which we have, in this particular case, when you're changing the angle, so now you're orbiting around a given object, right? So if you go back to the image which we had in terms of the potential, if you look back at the potential here, you could now think that here you are at a specific angle. So let's make a plot of that. So you could think of your origin here. Doesn't need to be the sun. And this is your object. This is your r min. And then you would be coming in something like this. And then you get deflected. And then you leave out again. So this is a hyperbola, right? And if we then take the angle, so this orbit is going to change here, right? Like a phi, like this. So if you now look at the solution, what happens here when the angle keeps changing? What kind of behavior would you expect? So does the radius go to infinity? Does it stay constant?
Yeah, I go to infinity.
Infinity. And this is actually one of the things you will observe when you look at your midterm calculations. So you're going to run things numerically. And when you then switch over to a force, which goes like 1 over the cube this relative distance, you're going to see a behavior like this. So when you want to interpret and comment the results, then you can actually go back to the analytical solution. Now, what you're going to do is more numerical exploration, but having the analytical solution allows you to ask these questions. What does this actually mean? Does that sound okay? Any questions to this? Okay, so I'm just giving you some hints and kind of ways to dig a little bit deeper. So the thing is that when you have a code which functions, we always want to understand what is happening here. So digging deeper is perhaps a trademark of being a physicist, being willing to dig deeper. And in this specific case, we are pretty lucky and we have analytical solutions. Now, I'm going to leave it to you to see what happens if this omega 0 is negative, because that will change the type of solution. Because when you have this type of solution with harmonic oscillations, you're going to get the exponentials with them. You can rewrite them as exponential with an imaginary argument. But if the omega changes sign, it's just going to be a sum over standard exponentials. So I'm going to leave that to you to analyze the behavior in terms of the analytical solution. But what you have is an analytical solution which you can use to interpret data. Okay, so I have some additional small things which I just wanted to mention to you so they can complete the picture a little bit. And some of these things are also related to homework number 9. So homework number 9 has a part which is a repeat of what we have seen, where you're asked to do some additional calculations. So let's look at a further example. And then we're going to dive into the Jupiter case in the midterm and how we can actually program that specific case. So let's take an example 3. And now we are back with the gravitational force, the standard one. So we look at our beautiful gravitational or Coulomb force, or anything which goes like distance squared, inverse distance squared. And then we assume simply that L is given. So we have made an experiment where we have been able to measure the angular momentum. So if you look up on Wikipedia, for instance, and you search for the angular momentum of the Earth, you will actually see that that is pretty well defined numerically. So we assume that L is given or fixed and mu is known. So these are parameters of the theory. Then what we have is our radial differential equation. So this is the radial acceleration, or what the quantity we call A of R. And this is again minus mu, and then I have a dv of d of r, and then I have plus r, and multiplied with phi dot. And then we remember that phi dot is equal to L divided by mu over r squared. And that means that what we have is an effective potential, which we are going to set up again, V of effective of r, which we can rewrite in terms of the angular momentum. So that's given by minus alpha of r plus 1/2 times mu. And then we have L squared divided by r squared. So this is the effective potential which we have. And then we want to find the radius of a circular motion. And now we are going to relate this radius of the circular motion to the type of orbit, to the angular momentum which we have. So we want to find, and this is where we have the minimum, the radius of a circular motion. So let me quickly repeat this, because this becomes also important for the midterm when you want to find the value for the radius which you're going to use. Now for the Sun-Earth system, we are going to assume that the radius, the distance between the Earth and the Sun, is fixed to 1 astronomical unit. But if we didn't know that, this is how you could fix the radius. So if we now want to find the radius of a circular orbit, what we do then, we know that this is, we found that this is where this effective potential has a minimum. So we are then saying that the radial acceleration is equal to 0. We found also that the angular acceleration is equal to 0. And that's why angular momentum is conserved. So what we have then is simply an equation which goes like 1 over mu of the derivative of the potential, where this is the potential here, V of R, d dr, and that's going to be equal to R times phi dot square. And then we can plug in the value for the angular momentum. So that means that what we have here is actually an L squared when we're plugging this in, divided by mu squared and R to the power of 4. And we know that this derivative here gives us alpha divided by mu over R squared. So this is going to be equal L squared divided by mu, and wait a moment, and this is multiplied with R actually, because we have an R from the expression here, that one. So that's the same which we have here. So that gives us mu squared over R cubed. And that simply means that this R min is equal to L squared divided by mu times alpha. So this means that I can go back, and we know that in this specific case, at the minimum here, what we have is that R dot is equal to 0, and that's equal to the force divided by mu. So this is just another way of rewriting it, of phi dot squared times R. And we know that this is equal to 0. So that means simply that phi dot times R squared is equal to alpha divided by R squared times mu. And that means that our phi dot, instead of writing that in terms of the angular momentum, we can now rewrite it in terms of the parameter of the potential, alpha. And this is for the gravitational force, this is equal to the gravitational constant times the two masses. So that gives us mu divided by R cubed. And then if I plug in R min here, then you get back to the standard expression, which we have seen many, many times. So this means now, so this is actually, sorry, this should actually be phi squared, sorry for that. So that means that our phi dot is equal to plus minus square root of alpha divided by mu times R cubed. And now I can go in and plug in R min here. I'm just plugging in the expression for that. And if I do that, I can find now that phi dot is equal to plus minus. When I plug it in here, I get an alpha squared times mu divided by L cubed. So why am I doing this exercise here? Now I'm doing this exercise because I want to do an additional thing, yeah? Yeah, actually in my notes, it says squared. And I was able to read off wrongly. Thanks. So we have many people with eagle eyes here, and that's good. Thanks. Now, why did I do this kind of strange exercise? So one thing is that I can actually now relate the angular velocity in terms of the physical parameters of the system. So I have the gravitational force constants, alpha, I have the mass, the reduced mass, and then I have an angular momentum, which I presumably can measure. So it's a fixed quantity. Now, let's go back to what we did with the harmonic oscillator, because now I'm going to expand a potential in terms of a Taylor expansion. You remember when we derived the equation for the harmonic oscillator, we actually took a Taylor expansion of the potential around the minimum. And then we had decided that around the minimum, the first derivative is 0. So we get a constant plus the first derivative, and then we have the second derivative. And that second derivative is something we identified with this constant k. Okay, so let's repeat that exercise and see what this can give us. So the question now is, suppose we got so hooked on this harmonic oscillator thing and the Taylor expansion we did, the question is, can we find an effective spring constant? And if we can do so, what does it actually mean? An effective spring constant at R min. So you remember what we did was to make a Taylor expansion when we looked at harmonic oscillations. We made a Taylor expansion around the minimum, harmonic oscillations. So we did a Taylor expansion, and what we had then is that this oscillator constant, or the spring constant as we called it, that is given by the second derivative of this effective potential with respect to R. And this is calculated at R is equal to R min. So remember now that what we did is to actually run the calculation at the minimum of D of R. And then we required simply that the first derivative is equal to 0. And then we use the second derivative to define an effective constant. And what we did next, when we derived this spring constant, was simply to ignore higher order derivatives. We simply assumed that this potential is well defined as a parabola, and that the higher order derivatives were just negligible, and we just ignore them. And then we defined this constant, K. Now, what we can do then is that if we now look at the force which we have, and we plug in, we go back now and look at the derivatives we had. So we know that the derivative, the first derivative is given by the equation which you see here. So this is the first operation we did. So what we are going to do now is simply to take the second derivative of this quantity here. And that second derivative, when we plug in the value for R min, is going to define this spring constant in a harmonic oscillator picture. So if I do that, so then what we are going to get then is the following. When I take the derivative and I set in R min, so this is going to be given by -2 times alpha divided by R min cubed. And then I'm going to have a plus of 3 of L squared divided by mu and multiplied with R min to the power of 4. And when I do the algebra at the end, I'm going to get this answer here of mu to the power of 3, alpha to the power of 4, and L to the power of 6, if I did my algebra correctly. Now, what we have next is the following. We can then define this omega 0. If we are thinking of harmonic oscillations around the minimum or the potential, so K divided by M, and if I do that, this is the same as alpha cubed divided by L3, and this is a phi dot, which we calculated above here. So we have that one up here. So this is our expression for phi dot. When I take the Taylor expansion of the harmonic oscillator of the potential and stop at second order, I find now that this angular frequency, which is actually the same as the angular velocity here, is the same as the derivative of phi with respect to t. So this means the following. If you now are thinking of your system and you're making small perturbations around the minimum, so this is your minimum here. So the potential goes up something like this, and then it goes like that. But we have made an approximation where we are looking at small perturbations or oscillations. Small oscillations around the minimum, around this R min. That means that what you have now is that these perturbations here, they oscillate with, or they could say they are in sync with the orbit. And so this traces an ellipse with a very small eccentricity. So you could now think of you doing a perturbation around the minimum. So that means that you will actually oscillate a little bit around the minimum here. And the frequency of oscillation is given by this omega 0. And you could think of that as an ellipse, which has a very, very small eccentricity. So you can actually make orbits where you're actually oscillating around the minimum, and that will correspond to an elliptical motion with a frequency which is given by your angular velocity here. So that's a kind of neat interpretation which you can make of your results. So these are kind of additional small things you can look at when you're thinking of your code, and you could make a small perturbation around a circular orbit. So the first 2 free exercises deal with circular orbits. And you could then think of what happens if I make a perturbation around this minimum of the potential. So you often, in physics, you often have a more complicated potential, and you will often look at perturbations around the minimum. And what you're doing then is that you're actually oscillating around this minimum. So there's a small perturbations around it. And then you could ask yourself, what kind of motion is this? In this specific case, the motion corresponds to an ellipse with a very, very small eccentricity. So that's the kind of interpretations which you can give to the physics here. Now, I wanted to end up with a discussion of the second part of the midterm, where we're going to simulate the solar system and add Jupiter to the Earth-Sun case. So let's just go back to one thing first. And this has to deal with where you can find the data for the positions and the velocities of the planets. So let's take a look at that. So if you go to the midterm and just scroll down here, and you look at the link which is down a little bit down here, there is a link to a NASA website, this link here, where you can then extract the information about the positions of the different planets. So this looks like this. So when you go to the link, this is what you are going to need. Now, this table produces data in different types. So you should go to the vector table. And in our case, we are going to look at the sun as our center. So when it says the coordinate center, that is going to be the sun here. Now, when you then click on that generate there, that's going to give you the initial velocities and positions of the planets at a given time. So you can actually specify the start time here. So if you want to, you could actually find the position of the planets when you were born. That's just an example. So if you click on that one, this is what it's going to produce. Actually, I already did it. So if you scroll down, this is the case of Mars. You can always change that. So you can change that so you have all the other planets. So if you click on edit here, you will get other option for the other planets. The thing which is of interest for you when you're going to look at things, if you now run calculations in Cartesian coordinates, you see now, so this is for Mars, on April the 6th, and this must be midnight, you can find the X, Y, and Z positions, and this should be in, I think, in kilometer. And then you have this similar thing for the velocities in the X, Y, and Z directions. Now, when you run your own program, you shouldn't feel constrained to use this, right? You can actually set up a circular orbit for all the planets if you want to, and just plug in the distance from the sun to the given planet. So you can run the calculations in 2 or in 3 dimensions. So this is very much up to you. And we've already said that this type of force, which we have, the gravitational force, forces you to have an elliptic motion in a plane. And that means that you could actually think of all the planets moving in a 2-dimensional plane. But if you want to, and it's not that difficult, you can add the Z direction as well. So let's see how we do that and what that means for our calculations. So let's go back to the whiteboard. So any questions about this? This is actually a beautiful site, actually. It contains a lot of information on different planets. So let's go back to the whiteboard and spend the rest of the time on the calculations you would typically do if you run this in 3 dimensions. So if you want to run in 3 dimensions, so what we have done till now, if you look at the Earth-Sun case, in 2dim. Then what we had is that the acceleration for the Earth. So f of x for this is the Earth. What we had is that f of x is actually given by the minus g times m dot of m of e, and this is divided by, if we're now dealing with 2 dimensions, x squared plus y squared, and then we have multiplied with x. So remember again that r in this case is just simply x times I plus y times the unit vector in the y direction. And similarly, we had an f of y, which is given by minus g of m times mass of the Earth. There's the mass of the sun times the mass of the Earth. So this is actually to the power of 3, x squared plus y squared to the power of 3 multiplied with y. Now, if you want to go in 3 dimensions, this is pretty simple. So if you want to extend this to a 3-dimensional problem, and then it's a little bit easier to use this data from NASA. So in the 3-dimensional case, you would need the z direction. And this is simply you setting up the force in the z direction. So you would have a variable z, but now you need to be a little bit careful because you would need to change r squared so that it includes the z direction. And you would have the same for f of x and f of y. Now, the differential equations which you got are dvx dt, and now we are dividing by the mass of the Earth, which is given by a of x, which is then given by minus g of m multiplied with x and divided by, and now I'm just writing r cubed. So r cubed is the square root of x squared plus y squared plus eventually c squared. And then we had a differential equation for d of x dt, which is given by v of x. And similarly, we had a dvy dt, which is the acceleration in the y direction, which is minus g of m dot times y divided by r cubed. And then similarly, we had a dy dt equal to v of y. So if we add the c direction, if we do that, then we would have a dvz of dt. That's the acceleration in the z direction. And that would be minus g of m dot times c divided by r cubed. And then you would have a dz dt is equal to vz. So you see now, when you increase from 2 dimensions to 3 dimensions, instead of having 4 coupled differential equations, you have now 6 coupled differential equations. So that's the only difference. And in your program, I recommend that you do everything in Cartesian coordinates. That's the simplest possible way of doing that. Then the only thing you need to add is the 3rd dimension. And the equations for the acceleration and the velocity and the position and so on, they are just the same. They are coupled because r depends on x, y, and z. So instead of having 4 coupled differential equations, you have 6. Now, if we add Jupiter, then we get 3 more variables. We would have, and then that means that we get now suddenly 6 plus 6 more. So we would have 12 coupled differential equations. And this just increases like that. So every new planet you add will give an additional set of coupled differential equations. So if you're familiar with object orientation, this is something which begs for object orientation, but you can actually plug in things by hand here. The only thing you have to be a little bit careful with the masses here of the different things. So this is actually a problem for those of you who are more programming aficionados and you love programming with objects and classes. This is something which really begs for that, because you can really simplify the code. And I see that some of you may have done it already. Somebody's done that? Yeah, I can see, I can see. Okay. Actually, normally when you run object orientations in classes, you have this boring ticket booking systems and so on. But this is actually one of these physics cases, which is really begs for that. Okay, so I see I'm running out of time. I'm going to sneak in 2-3 minutes to show you how you do Jupyter on Friday, so that you have the essentially what you need to solve the midterm. Any questions, guys? Before we meet again on Friday, and please feel free to hang around if you want to. Okay, I'm going to stop the recording for everybody.